solving trigonometric equations with multiple angles. So you see the multi-angle situation when there's a coefficient there, and in the past you might know we've called that coefficient b, which affects the period, and so the higher the b, the value of b, the more compressed the function is. And just a quick bit of a revision, if we look at, oh by the way, we're looking at cos 3 theta equals square root of 3 on 2 between 0 and 2 pi, and we're solving for theta. So if we look at a graph of it, this should be familiar territory based on our previous study. I've graphed cos theta for a reference, cos 3 theta, and then the horizontal line y equals square root of 3 on 2, which is about 0.866. And you can see there the blue function, the red function cos, has fewer points of intersection or fewer solutions than the y equals cos 3x curve. Alright, so that makes sense, doesn't it? It's more compressed, so there'll be more solutions once we increase this number here beyond the standard 1. So keep that in mind, you should expect more solutions. In fact, when this value b is 3, usually for cos we'll get triple the number of solutions. So instead of maybe 2, there'll be 6. It does depend on a few other things, but we'll see as we go. So what we do is make a substitution. We let 3 theta equal something else like x. So let 3 theta equal x. So we'll do that substitution. By the way, that means theta equals 1/3 of x, or x over 3, which we're going to use a little bit later on. So we have, in other words, cos of x equals root 3 on 2. We know that it is an exact value, and so therefore the angle, the acute angle we're talking about, is pi on 6 from our table of exact values that we should know very, very well. And the acute angle there also is pi on 6 because we know how the unit circle works by now. So cos is positive in quadrants 1 and 4 in this case. So the actual angles we're looking at are pi on 6 or 2 pi minus pi on 6, which is 11 pi on 6. So just putting aside the matter of the restricted domain at this stage, it basically means we'll have solutions, coterminal solutions every time x equals pi on 6, or x equals 11 pi on 6, but how do we account for the increasing number of rotations, revolutions around? So we need to add something else in here. So we're going to squeeze in something else. So I need to move my or out the way. So let's put or there. It happens every rotation, so what we're going to do is add in 2k pi. So 2k pi is going to be put in. We've also got 11 pi on 6 plus 2k pi, where k is an integer. So you can use integer values, whatever you like, but it makes sense to start at 0. So what does that look like then for theta? Well, we've got that substitution we did above, where we can see just up there theta is 1/3 of x. So basically we need to divide these above expressions by 3. So that would be pi on 6 plus 2k pi over 3. and same with the other one. Plus 2k pi all over 3 based on our substitution we just made. And we've got pi on 18 plus 2k pi over 3. Here we've got 11 pi on 18 plus 2k pi over 3. Okay, so we've got we've made allowances for going around the unit circle an integer number of times, and that will generate all of our solutions, and we'll have to check whether they're basically still in the restricted domain at the end. Also, we're back dealing in terms of theta again and not x. X was just a temporary substitution. So for the domain, it said 0 to 2 pi. I've converted that into 18ths because that's convenient there. And so when k equals 0, we look at how we generate the specific solutions here. So we've got pi on 18 plus 2 times 0 times pi on 3, which is just remains at pi on 18. Okay, so again we're using this line here, it's key. That line there is really important because it's what we're using to generate this as we increase k. Alright, so we've got pi on 18 and then we've also got theta equals 11 pi on 18 as well. Now let's make k equal to 1. So again, that yellow line of working there, k is going to be equal to 1. So we'll have pi on 18 plus 2 pi on 3, because k equals 1. So 2/3 pi. Now that's got to multiply numerator and denominator by 6, so that's 12 pi on 18. So 1 and 12 is 13 pi on 18. So 13 pi on 18 there. This one over on the other side here, give yourself plenty of room when you do these questions, as you can see. And we've got 11 pi on 18 plus 2 pi on 3. And 2 pi on 3, remember, is 12 pi on 18, so we've got 12 and 11, it's 23 pi on 18. When k equals 2, theta equals pi on 18, so that's 4 pi on 3 added on now, plus 4 pi on 3, and we get 25 pi on 18, and theta also, come back, theta equals 11 pi on 18 plus 4 pi on 3, and that's 35 pi on 18. Okay, now let's look, we've got to keep a bit of an eye out. Are we going beyond our end of our domain here? All these values are clearly above 0. 36 pi on 18, can't overshoot that, or we'll be outside of our restriction. So we keep going. We've got up to 35, although it should be like, we must be feeling like we're getting pretty close to the end now. But do check. So the next one is pi on 18 plus 6 pi on 3 now, because k equals 3. 6 pi on 3, that's actually 2 pi. So 2 pi is a limit. If we add anything on, it'll be too large. So that's not a solution for this particular situation because of the domain. And look, it's going to be pretty obvious. We're only pi on 18 away. So, but just for the justification of it, just jotting down, just clearly showing that 11 pi on 18 plus 6 pi on 3, aka 2 pi, that's too large. So that's not a solution. So that's it. So theta is the solution. Theta has 6 solutions. Remember I said before, normally if b was equal to 1, it wasn't a multi-angle, you'd have one solution. We had b equal to 2 solutions, but we got b equals 3, so it's 2 by 3, which is 6. So that seems pretty reasonable. So we put our solutions in, and we see it written in there. For the second and final one, I'll go a little bit quicker. We've got something that doesn't look like an equation, but if we rearrange it and make a substitution, we'll be hunky-dory. So if we firstly let 2x, or say some other symbol, I'm going to call the other symbol theta, let theta equal 2x, or in other words, x is theta on 2 for later on. We've now got sine theta equals 1.5 cos theta. That's not so bad because we can go sine theta over cos theta equals 1.5 because I've divided both sides by cos theta. And if we look at our identities, that means tan theta equals 1.5. And if we find the inverse tan of 1.5 for an acute angle, we can use our calculator because that doesn't correspond with one of the exact values from the table. So that would mean that theta is 0.9828 if you grab your calculator, and we're in radians. Alright, so if we put in a sketch, always recommend a quick sketch of the unit circle, and it helps justify your work too. So tan is positive in quadrant 1 and quadrant 3, so these are the positions of the angle 0.9828 radians there, and also there. Okay, so we've got the actual angle then. Basically theta equals 0.9828 because it's in the first quadrant, and we've also got theta is pi plus 0.9828. And we can calculate that like so. So theta in general equals 0.9828 plus 2k pi when theta is 4.1244 plus 2k pi, where k is an integer. And we need to substitute back in terms of x. To get back to x, it's theta on 2, so that provides us with x equals 0.9828 plus 2k pi over 2, because b was 2 this time, and x equals 4.1244 plus 2k pi over 2 those values there. Notice how it's plus k pi because of the divide by 2. So let's cycle through and make k start at 0, which is a sensible choice, and we have x equals clearly 4914 there, and x equals 2.0622, and generate k equals 1, where that's just adding pi on, so we've got x equals that 0.4914 plus pi. So I'm not going to write the whole calculation down just to save a bit of time in the video, but you probably should. So we just got to add pi onto 2.0622 and we get 5.2038. Okay, keep an eye out on the domain restriction. It was 0 to 2 pi radians, so 2 pi is about 6.28. So we haven't reached that stage yet, so we can keep going. We're after probably 4. If we look at it, although 10 is different with the number of solutions, so if the sine or cos, we'd be looking for 4 most likely, but 10 isn't always that way, but as we'll see in a minute. Or if not, we'll see it on the next video. Okay, and we try for k equals 2, but they both yield values that are too large. So we've got our 4 solutions and we write them down explicitly, as you can see.